Good afternoon, folks. I'm a student of the course 4006. Here we are. We're going to be talking a little bit today about numerical differentiation and uh, and why we going to be talking about that is because sometimes uh, getting the derivative of a function might be a little bit hard, and since the only thing that you are interested is in try to get this average value here. So why we don't use, for example, numerical differentiation? That will do. But the question is where we start to do that. Before doing that, you probably remember this table. This table is from Chapra's book, and it's sort of kind of a summary, like where it shows you the formula that you need to use for trapezoidal rule, which is here for only n equal 1, and eventually what will be the truncation error for n equal 1, but I put nearby the formula for when n is above 1. In that case, you will go with this one, and this one requires the average of the second derivative, which if you are following this series of videos, that means it's the first derivative, because just to make the story short, when you are talking about the average of the second derivative is just, if I write the whole thing, that will be the second derivative, the integral of the second derivative between a and b divided by b minus a, which eventually the integral of the second derivative is obviously the first derivative of a. In this case, let's call it of x. That's no problem. That evaluated between a and b divided by b minus a. As you can see, so that actually I don't need the second derivative. I just need the first derivative of the function. Evaluate that function between b and a, and that will provide, if I move this a little bit weird where it is, so that will provide me the average of the second derivative. Is the evaluation of the first one within the limit a and b divided by b minus a, and that, folks, is what we call the average of, and that would be the average of the second derivative, and that's it. All right, so the same, likewise, on Simpson 1/3 here, it shows the formula for only one application, and this is the error for only one application, but nearby I have the formula for Simpson composite when n is either, in this case, 4, 6, is a even number, right, for n value. So it's the same, basically, but then if you need the average of the fourth derivative, I can write it like this. That will be the integral of the fourth derivative with respect to x dx, missing the dx here, sorry for that, and evaluated between a and b divided by b minus a. So what's going to be happening is you pretty much have already the idea. Let me get this right. What's going to happen is that the integral of the fourth derivative is the third derivative. So you only need here is the third derivative of x evaluated at the limit a and b divided by b minus a. So if I want to apply the truncation error, either let's say to Simpson composite, I only need the third derivative. If I, on the other hand, I want to apply trapezoidal rule, I need just the first derivative, which mostly is easy. In most cases, the first derivative is straightforward. But then the second is get kind of a little bit more complicated, and and when you get to by the third, things are kind of nasty already. So what we're going to do is apply then numerical differentiation. By definition of any calculus book, you will find many times that if you have a function f of x like this, the derivative of that function f prime of x is equal at f evaluated x plus h, where h is a very small number, minus f of x divided by h. And this is right. This is what is called forward differentiation. I mean, there's backward differentiation and this central differentiation, right? So pick one. Let's fix this so it looks better. I'm going to be using forward differentiation, although central differentiation will be better because how good is this is to the order of h. Now, if I use central differentiation for my first derivative, that would be as good as h squared. So it's better to use central differentiation. But again, I'm going to be using forward differentiation on this example. It works okay. It works perfect. I don't have any problem with that. So if this is the definition of the first derivative, what would be the definition of the second? You will find out that it's as simple as doing this. The differentiation of the second derivative by definition will be the first derivative, the first evaluated x plus h minus f prime, which is the first derivative evaluated at x divided by h. And you keep going. I mean, that's the first, this is the second. What would be the third? Would be the same. So the formula on its own is only changed. You are increasing, I mean, the derivative is going forward as you keep going here. Now, before doing that, let's understand what is this, f prime x plus h, because that has to come from here. If I do that, like for example, what is f prime x plus h? It's as simple as substituting x plus h here and see what's happening. So that would be x parentheses down. You have x plus h, so you are putting all this on where is x. So what happened with the h? So you will have x plus 2h. That's what's happening. See? So, and then what else you have for this? Minus f, what is on x? Then x is again x plus h, and all that divided by h. All right, that was this definition of this. How about this? Well, that's already done. That definition is already here. So to get the second derivative right, you only need to do this formula here, which is based on the first one as well. So let's do that. So that would be f x plus 2h minus f x plus h divided by h minus, I'm doing this definition here, right? So f prime is already defined here. If I do that, that would be f x plus h minus f of x. Careful here, right? Because this minus is right here. So, and that divided by h. So I did this part, which is this one. I did this part, which is this one. And now everything divided by this h. So when you, simplify the whole thing, so the second derivative is nothing else than this number, this here, this f of x plus 2h. There's nothing here that has similar with a similar value. So that's it's all alone. So I have f x plus 2h. Now, this one is negative here, but this one is negative as well, and they are identical. So minus minus, that would be plus 2. Sorry for that. It's not plus, it's minus, right? Negative and negative. That would be minus 2f f of x plus h. Now, I have this negative and this negative right? That would be a positive. Remember, everything is under h, but there's another h here. So that would be h squared. All right, there we go. So first derivative is this one here, no big deal. It's just the definition of the derivative using the forward definition. And this is the second derivative using the definition of forward derivative as well. So if I'm doing, for example, if I'm doing truncation error, it's more than enough. With this will be okay. That's all what I need. This for trapezoidal rule. Now, if I'm doing Simpson composite or Simpson 1/3, well, that's another story because I will have to keep going. And right now, I'm in the second derivative you are seeing here. So let's do the third derivative. So the third derivative of x, by definition, is just the second derivative. Hold it for a second here. Yep. Second derivative of x plus h minus f of x, second derivative, divided by h. As I did before, you only need, let's fix this. You only need this new definition to plug it here. So let's do that. So the second derivative on for x plus h by definition will be, now anywhere where you see the x, you will plug x plus h. That means that here you will end up with f x plus 3h now minus 2f x plus 2h, and now the last one plus fx plus h, and the whole thing divided by h squared. So what I need to do is apply this definition for the third derivative, and that will be the third derivative of a function with respect to x will be plugging all this. If you allow me to copy that, oops, I'm not sure whether I copy or not. Well, let's do it again. Copy, and now it's yes. And let's put it somewhere here so I can get some more space. Paste, and let's reduce it a little bit more. And now let's bring this part that is here. All right, this part here is the definition of this part here of the second derivative, but I need the x plus h. Now I need to do this part here, minus f of x. So, but that's actually the second derivative of is this one here. So let me, all right. So that will be taking all these and plug it here, and then finally dividing by this h. So the second derivative is this one here. So let's get all these and put it right here. All right, and everything obviously has to be divided by h. So this part here is the definition of this here, the second derivative evaluated x plus h, and this part here is the second derivative evaluated at x only. So with that said, let's see, the third derivative finally, let's see what comes together. This one is alone. So that means f x plus 3h, there's nothing there. Now, this one is negative, and this one is negative as well. It's the same x plus 2h, same x plus 2h. That means minus 3f x plus 2h. Now, how about this one? This one here is positive, and there's a negative here with a negative here. That will make this part here positive 2, and this is 1, so I have plus 3 f of x plus h. Now, there's a negative here with a negative here, with a positive here. That will make this minus f of x, and the whole thing divided by h to the cube. See? And that's how this, if I'm only interested in the third derivative because of this, because I'm using the average, the average for the fourth derivative is the evaluation of the third derivative within the limit a and b divided by b minus a. That would be okay. This is it. This is the only thing that I need. That's my third derivative. I will go one more just in case. This is the fourth derivative, just to see if a pattern kind of show up. Kind of curious what this eventually will looks like. So the fourth derivative here will be of x will be obviously the third derivative of x plus h minus the third derivative of f of x, and the whole thing divided by h. So here we are. I need, again, the third derivative, which is all this, because it has to be evaluated now in x plus h. So will that will looks like this. Let's put it right here. The third derivative of x plus h equal. Now, plug x plus h here, because this is of x not only. So x plus h, that will be f of x plus 3h plus 1h here, that will be 4h. All right, minus 3f parentheses, and here we go. X plus h, that will be x plus 3h, and then plus 3f x plus h, that will be x plus 2h, minus f of x minus f of x plus h, and the whole thing divided by h to the cube. All right, that's f of x plus h. F of the third derivative of x is just this one here. So let's apply the definition of the fourth derivative. Let's do it here. That will be all this part here. This is what I like about the surface. You can, when I do things twice. Let's put it here. I fix everything else later. Let me move where it is. Right there, and let's make it smaller so I can plug the other part. So let's fix this, and that will be minus f of x, but that would be this one here. These definitions, the definition of the third derivative, which is way up here, that one there, because that's this part here is this one here. So if I do that, I picked all this. Let me pick all this. Let's copy that and plug that right here. Mhm. See if I can do it. There we go. Paste. It's a little bit too big. Let's make it smaller so it looks the same size as the other. All right, I'm applying now the definition, and everything has to be divided by h. There we go. And this is the fourth derivative, and let's see whether a pattern emerge. Let's see. So I got the 4, so this fourth derivative is equal to f evaluated at x plus 4h. Now, I got a minus 3 here, a minus 3, 3 x plus 3h, and there's a minus here. Remember, this have a parenthesis here just to be sure. This has x plus 3h, x plus 3h. This is negative, and that will be negative, so end up being minus 4 f x plus 3h. Now, I have these 3 minus minus, that will be plus, and that will be plus 6 f x plus 2h. And how about this one? Minus here, minus with that one, that will be 3, that will be minus 3, and this is, so that will be minus 4. Minus 4, minus 4f, hold on for 1 second, fix this, f of x plus h, and minus minus, that would be plus f of x. Well, I don't know. I don't see a pattern coming out, and that would be h to the, that would be h to the 4. And let's fix the whole thing so it looks better. H to the 4, and that one that is way up there, let's put it where it is. Here we go. There's a pattern here. I don't know. It's a little, well, I mean, I can see this one coming strong, like for example from the third derivative. Let's see, where is it? The third derivative, I got these. For the fourth derivative, I got these. You see the 4h there, and now there's a 4 here for the f3x plus 3h, and here you see a 3 and less than this number. See, this is a 4 and this is a 3. Here, no, that's where things start to get kind of weird, because that would be x plus h. That's a 3 there, and now I end up with this in the middle. I will, you know, let me think about it. I will not say that there's a pattern here. I guess that you have to kind of walk, you know, the whole thing. If you are interested, like for example, in the fifth derivative, numerical derivative, what would that be? Then you will have to work this out, like the fourth derivative of x plus h minus the fourth derivative of x over h. So, you know, you keep adding this pattern as you go along, and I guess that would not be a big deal to get the fifth numerical derivative. But again, I think that I'm getting a little bit tired of this, of doing this. So I will say, let me summarize here. Let's see if I can summarize nice and easy. So if you are interested only on the first derivative, copy, let's put it somewhere that I can see them, watch them all, you know, all together. That's the first. How about the second? Let's copy the second here without any other stuff. If I copy other stuff, I erase it. Let's see, copy, and let's put this one here, paste, and let's erase what I don't want. First, second, let's get third derivative right here. Okay, let's see if I can get it through this. No. It's gonna get ugly as well. Okay, I erase whatever is not required. Copy. And let's put that here. And let's make it smaller. So I don't need this. I don't need this either. So first, second, and third. How about the fourth one? Okay, fourth derivative. Numerical differentiation at best. And this is the fourth derivative. Copy. Put it right here. Make it smaller. Well, now that's not that smaller. Well, I can still see everything. All right. So, one thing I could certainly do now that I have all them together. Copy. Here we go. Now let's pop this big, and let's make perhaps this smaller so that we can have all of them. The idea is to have it like that, is that you can now take them to Excel and do whatever you have to do. There we go. So these are all forward differentiation because I use this for my definition, a forward differentiation or derivative, the way I'm doing this, and they are all of the order of h. You can do better, but again, I think that this is good enough for what I need. In fact, I only need to the third derivative. I got to the fourth just for the sake of the argument. You can keep going and so forth. Why you might want to keep going? Well, let's go back for 1 second. I mentioned a few things here and there, but I didn't mention something I think it has to do with this. Let's pop this big. I got up to Simpson 3a. I mean, that's the fourth derivative, which basically you need the third derivative. But how about this one? If you are in Boole's rule, require the sixth derivative. That means I need to get into the fifth derivative to get this right. So, I mean, Boole's rule will require, I mean, again, if you are talking about getting or doing this problem, you know, using the truncation error estimate, you certainly can do that. How about now if we test the whole thing with well, now something that is kind of straightforward that we can all agree to see whether this derivative makes sense. Let's go to the next page here. Let's go here and so, like for example, how about if we say a very simple one? Well, not so simple. I mean, I want to use something like, let's say that f of x for testing is x e to the x. I mean, that's simple enough. It gets cumbersome as you get many derivatives or all the derivation that you might want to go through. But for the first derivative, that's simple. F of x is the derivative of the first one. That would be 1 times a to the x plus x times the derivative of the second, e to the x. That's the chain rule, and that will be ex 1 plus x. Good enough. How about the second derivative? You can go through either. I mean, you can use this one, or you can go here. Let's do from here. That would be e to the x is e to the x plus, but this one is repeating itself. It's this one, right? So that will be this result again. So that would be ex plus x e to the x. If you check this, that would be ex, and this ex, so that will be 2 plus x, right? There's a pattern kind of developing right here. So that will be ex ex, that would be 2ex, and then ex times x, that would be this one. So the third derivative of x will be, let's see, e to the x plus e to the x plus, here again is this part here, so that would be ex plus x ex equal, get ex as a factor, and then you have 1, 2, 3 plus x. So you can clearly see there's a pattern that is being kind of that developed doing this derivative. So the last one, the fourth derivative of this, I mean, you can jump here, or you can use this one if you don't believe me. Ex plus ex plus ex. What about this one? It's that one again. Just write it down. Ex plus x ex. So that will be ex. How about now? 1, 2, 3, 4. That would be a 4 plus x. We're done. And that's the fourth derivative. So, how you want to use this? Like, for example, let's say that we want to integrate. I mean, when I put together this, this function, is because I will be integrating something like this. Let's see. Let's say that I want to integrate that function between 0 and 4. All right. So this is an integration by part. Extremely straightforward to do this. Should I do it? Yeah, let's do it right here. Like, for example, there's a decision. This is integration by parts, and there's a decision you have to make. There's, I would say, I call it mnemonics. That is, goes like this.
We interrupt this program to bring you a special report.
So let me explain a little bit, this issue about integration by part. And integration by part goes through this formula shown here, and it applies to, for example, to the sample that we are studying, like is x times the exponent of x dx. And the issue is how we define what is u, right? And we go through these mnemonics, and it says that the best definition for u will be like if there's an inverse function here, like arc sine or arc cosine, etc., that should be the definition for u. Versus if there's logarithm, then we use logarithm. Algebraic, like x squared, like a polynomial, that will be next. If you check here, that's what we have here, an x, and that's, if you check, then after that algebraic will go trigonometric, like sine, cosine, and finally exponential, like x e to the x, also and so forth. So as you can see, that's why this x was assigned to u, because on the order for u definition, the algebraic comes first than the exponential. So that's why u is assigned to x, and what is left is ex dx, and that's assigned to dv, which is basically this part here. And it clearly says that if you know u, you need to multiply that by b, which will be the integration of this part, and then you end up with this final integration, and that's it. I hope you understand where that really means. This mnemonics really means. Thanks. So that means for the definition of u, you rather use x here. So that means that dv on this will be then the other stuff, ex dx. Now, what happened here? You differentiate that. That would be dx. And how about here? That would be an integral. You need to do the integral part. But the integral of ex is ex. Not a big deal. So the final solution of this will be x and b. That will be the integral of, that would be x e to the x minus the integral of this times this. That will be the integral of ex dx. So the final result of this will be xex minus ex. And that's it. But evaluate it. Now we need to evaluate this between 0 and 4. And that will be the result. The analytical result will be, like, for example, 4 e to the 4 minus e to the 4 minus, when x is 0, this part cannot die because of this x, but you still have this one. So that would be minus e to the 0. And the final result will look something like, that would be 3 e to the 4 minus that would be plus 1. So that's the analytical result that we are looking into this problem. If I do this integration by parts, as I'm showing here, the question is, this will be the true analytical result. Now the question is, would I use Simpson? Would I use trapezoidal rule? Let's use Simpson. I want to get to the third derivative and see what good value of n I should be using. All right, and let's demonstrate that. And if I'm going to use Simpson, the next things that I need to specify was the truncation error, the approximate truncation error that I'm going to be using for this problem. Let's say the approximate value is 0.00. Let's give another 0, 3 very good decimal places. How about a 1 here? That will do. So if I go back to the formula for my this one here, let's see. I need this. That's all what I need. Let's see. All right. So that value, absolute value of that, has to be less or equal 0.0001. So from here, we're going to get our n value. And that's what we're going to be trying to do. But for that, we need the average of the fourth derivative, which is basically the evaluation of the third derivative, and so forth. So I guess that's way too much theory already. Let's get our hands busy, and let me see what I need. I think what I need is, first of all, let's demonstrate that this really works. I mean, that this makes sense, this part here, the part of the derivative. And then we move to the part of the integrals, or the integral. All right, so let's copy this. And we're going to go to Excel for doing some demonstration and, you know, trying to figure out how this looks like. All right. Should I copy that? Yeah. All right. Go to Excel now. All right. So here we are in Excel. Let's paste all that work that we did on one note. Here it is. Perfect. And let's see how we do this. All right, here we are. Let me see, like, for example, one thing that we certainly can do, let's say this is, let's define some value here. For x, let's say that we want to work this around 1. For h, let's pick a value small enough, 0.001. And I was playing around a little bit with Excel doing adding function, and let's see if we can add one here. Let's go to, and that function would be sort of f of x, which is this. So it makes life easier when we want to punch all this there. So let's go to developer, visual, open this, and here we are. And let's hit a right click just to insert a module. And here on this module, we'll insert a function. Let's see if this works. Function f, and that function will be a function of x. And what will be the function? F equal x times the exponent of x, and that will do. Let's see if I return back, close and return back. That should be there. And all right, f. So if we want to do f1, which will be the first derivative, I should be able to get f. Let's see, equal f. There we go. It's right there. See, good. F of now, that will be x. Where's the x? Is this one? Sorry, x, this one, plus h minus f of x, which is this one. Now I need to put parenthesis here because all of that will be divided by h, this value here. Well, if that number makes sense or is right, should be close to this one, which that would be the first derivative. Let's work that out. That would be equal exponent of x, which is this value here, times 1 plus x times 1 plus x. Good. About, yeah, two decimal places, 5.44. I can't complain. That's good. How about f2, the second derivative? Well, that's becoming a little bit kind of boring to input all that fx. I had to pick all this from above. That's gonna take a while. Let's do more like we will do actually, regular math. Like, for example, let's define this value. That is x. Instead of calling b1, let's call x. How about this one? That would be h. So, that's, I said, usual name is x, right? Enter. How about you? H, and that's x. Good. So we got that straight. Now, how about here? Let's test. Let's test this. F is working perfect. So let's put f x plus h. Let's do that. X, only a test, plus h. I'm talking about the second derivative. So this actually, let's say 2 times exactly what is there. So I don't massage or do any gymnastic with it. It's just the way it's shown here. X plus 2. Let's see if it works. Perfect. It's working. It's picking the value right here the way I named them. So if I continue with this formula, that would be minus f of what? Minus 2 times x plus h. X, I love this, plus h. I don't have to punch any number, just variables the way it is right here. Plus f of x. There's a parenthesis that I have to wash out for that. It's this one. And the whole thing divided by what? H squared. So that means h square. If everything look good. No, everything doesn't look good. I'm missing something. Let's fix it. Let's fix what it is. X plus 2h, that's okay. Oh, here is missing the minus here. Minus 2f x plus h, yeah, plus f of x, everything divided by h squared. It seems like now it's correct. Excellent. So if I drop this, but before dropping that, let's fix here and fix this value as well. And remember, the second derivative is pretty much like this one. Why I'm having this problem here? There we go. There we go. It's like this one, except that they said 2 here. Well, 2 of 2, we are hitting that one right. How about the third one? F of the third derivative of that function. That will be, actually, let's pull this one down and let's fix whatever needs to be fixed. That's a 3h here. How about the other one? That's minus 3, but that's x plus 2h, so it's a 2 here. Plus 3, but here is x plus h, and now this minus f of x, minus f of x. Let's see. Yes, that's correct. Minus, yeah. Minus 3 plus 3 minus fx. Now this h is to the cube. Let's see. Enter. Now let's get this done. Oops. Fix this. That's the third derivative. That's a 3 here. Excellent. 10.87. No bad. 10.89. Could get better. Remember, we are doing forward differentiation. Maybe the error is basically to the third decimal place. 1, 2, the first two pretty much close. So it's about the order of this. You want better, more precision. You have to use kind of a central differentiation, and that will do better, a lot better, because that would be h2 squared, the precision on that one. So the fourth derivative, let's see the fourth. Actually, for the fourth, let's drop this and let's fix what needs to be fixed. This is going to take a while. That's a 4h. That's 4. And then minus 4. And inside is a 3. The next one is a 6. And that's a 2 times h here. And I'm going through this one. Now I need a minus. That's a 4 here, right in front. And inside is x plus h. And let's see, x plus h plus f of x plus f of x, and that's h to the 4. Wow. Let's see, 4h minus 4, plus 6 2h, yep, minus 4 x plus h, yep, plus f of x, h to the 4, divided by h to the 4. Look good. There's a pattern. I mean, it's going up. Good. So this should go up as well. Oops. Fourth derivative. This should be a 4 here, according to the fourth derivative. Right here. And when I do that, 13.59. Well, what can I say? I mean, it's pretty good. I would say more than what I expected for this fourth derivative. In fact, let's see. Truncation error will be a huge problem. Let's see. I mean, just because of Excel round up error internally, that would be if I take that number and get that number to to the fourth power times 10 to the 12 minus 12, 10 to the minus 12. I don't know. If I reduce that number, I might be in problem. Let's see, but that would be way too much. Yeah, I imagine that. Check this out. You see, I try to improve the number, but I'm having trouble with the fourth derivative. The other one are okay. In fact, they might get better and better precision, the up to the third derivative on this particular function. But now, not so quite on the last one. I mean, in reducing the h value would not, it didn't improve much. In fact, I depart from the real value. So let's go back to what I have before. So that would do. So in other words, this is the third derivative evaluated at 1. Now, for my, let's see, let's go back to OneNote for 1 second. And this is what I have. Let's see, all this theory here. So the average here that I need, if you remember that, I need to do that calculation based on the fact that the average of the fourth derivative is basically the third derivative evaluated in this case between 0 and 4, because that's the integral, right? 0 and 4, divided by 4 minus 0, that's 4. So I need the third derivative evaluated at 4 and the third derivative evaluated at 0. All right, let's do that. Let's go back to Excel. And now that we demonstrate that this kind of work, so I can certainly do that. And let's see. Like for example, x equals 4. Numbers should change altogether. And no bad. See? Fourth derivative is about, I mean, I have it here, but I will use this number because that's a numerical, the derivative I got it from a numerical value. So that would be 382. So my third derivative evaluated at 4 was, copy this number, and when you paste a number there, this. Now you need the third derivative when x is 0. All right, so when you finally plug 0 here, you get, it's interesting, for around x equals 0, that's a 3. That's a perfect. So you get 3 here. Now what you need to do is the difference between both. Let's get that here. That will be this one minus this one, and all of that divided by 4. And that's finally the average, the fourth derivative, the average. The average value finally is 94.96, and that number is the one that we're going to plug in our formula to get our n value. Let's do that. So our value of the fourth derivative for that function eventually end up being 94.9608. So the only thing that we need now is to get our n value and that absolute value. So that will be 1 over 180 and divided by 0.0001, and b minus a, that would be 4 minus 0, that's 4 to the 5th power, and let's see, 1 2 3, yeah, and that's a 1, and that multiplied by 94.9608, that's the average value for the fourth derivative, and that has to be all that, right? I mean, absolute value. I'm gonna keep this. Gotta be less than n to the 4 power. Oops, n to the 4. So finally, the n value, if we work all this in Excel, let me do that. Remember, I need to get the 1/4, the root of this guy. So let me do that in Excel. Control copy. So we move to Excel somewhere here. So I can do that. Let's put it somewhere here. Paste. Sometime. Here we go. Paste special. And reduce it so that they look good. So I can do it right here. So the value of n that I'm looking equal, I'm gonna put a parenthesis because I'm gonna be using for the getting the 1/4 here. So that would be 4 to the 5th times 94.9608. Actually, you can pick. I don't know why. If it's here, right? Yes, that's it. It's more simple. And all that divided by 180, which is also divided by the truncation error, which is 0.0001. And now close that parenthesis and get all that to 1/4. The 1/4 power, and let's see if I got everything right. Wow, that's a big N for that. Let's see. Yes, it is a big N indeed. Basically, remember, I want a truncation error to be less than 0.0001. That means that if I use 48, I will not get that, but if I use 50, I will get more. So I guess this case I'm using Simpson composite, so that means that n will have to be 50. Cannot use 49, so that I need to use n equal 50 to get a lot of precision. Let's pop this open big and let's test that theory. Let's see if n equal 50 will do the trick. Let's start by A and B as always. You know, A 0, B 4, N. You know, I put this in order. 50. Oops, sorry for that. Way too much. 50, 50, 50. Where is the 50? Right here. And delta x, that would be, for my integral, b minus equal, that would be b minus a, b minus a, b minus a over this value here. So here we are. Let's do this quick and let's see. First of all, I'm going to put here an n value where I'm going through, you know, or the n box or whatever you want to call this. And let's call this here x, and let's call this one f of x. And the last column is the actual area for Simpson composite. All right. This is 0. We are starting on 0. X is the first value, is a. Oops. Is the first value. That's here. And f of x is just the function. Is this times the exponent of that value. And the area under the Simpson. Remember, this go the way it is right there. Now, this needs to be multiplied by 4, and then by 2, and by 4. But let's figure it out a way that Excel will do that for us. So let's say that this goes on a plus 1 basis, and x here, that's actually the delta x, that goes plus delta x here. And if I drop these, And I need to figure out the way that I'm going to be multiplying this by 4 and so forth, or by 2. So let's see how this works. Oops, let's see what happened here. Oh, missing the dollars. Here we go. Now let's fix it. Let's see if it start to pick. Yeah, now it's working. So let's see. Let's go here. Okay, gotta go further on this. Let's see. Oops, I overdid it. 50, where's the 50? Right there. See, when I hit the 4. So all these gotta be clear. Clear content. Now it looks better. So imagine yourself writing here by 2, by 4, by 2, by 4. That's way too much. Let's do a function here. If. Now we go here and let's see. Integer, and now we're gonna make an equation here that will do the trick. Like for example, it's gonna test for odd or even. It's very easy. If you do 1, that number there, and you divide that by 2, and then you close that, and then you multiply by 2, and then if you subtract this value, and if that logical test, let's see how this go. I think I might need another parenthesis here. Let's see. And then if that, all that math actually, let's see, this parenthesis with this one and this one with this one equal 0, then we move to the value if true. What is the value if it's true? If it's 0, it means that it's even. So it means that I take this number and multiply that number by 2. Now, if it's false, like right now, it's going to be false, I take this number and multiply that by 4. Now, that close up parenthesis, I think that I have the required parentheses. That will do. Let's see. That's the number. The next thing is just drop this to here. And you know that this has to be multiplied by 4. This is an odd number. So that means this number has to be multiplied by 4. You want to check that out. Let's check it. This time 4. Yeah, perfect. So, and this just goes the way it is. And now the sum equal. The big sum of everything equal of this to here. And that has to be multiplied by delta x over 3. Finally, I got the number. That's the number. Let's put more decimal places. And let's get the real number. The true number was somewhere here. Right here. Let's get it somewhere here. Base special. Wow. Let's see if I get this. 3 exponent to the 4 plus 1. So let's do this right there. So it's 3 times the exponent of the value of 3 plus 1. Oops, sorry, to the 4. I said, oof, what happened? There we go. Now, let's see the difference. Equal. This is the real number minus this. Ooh, that was perfect. This is what I call, this is the area using Simpson composite, and this is the area, the real area. Let's put the real area. And finally, and this is the error, the what we call it ET, the truncation through error. That was perfect. 0.000, this will become a 1, and that will do. That was perfect. I mean, that's textbook. That's, we got it. And we did finally, and we did all this with uh, numerical derivations, which are shown here. And what I did with this numerical derivation was using the forward definition of a derivative, and from there I did the others. All right, took me a while, but you know, that's how it goes. But I like it. Very good precision with 50. A lot. I mean, now, I mean, there's a lot of effort because, as you can see, I mean, I derived this, but if you use it the way they are here and you plug them for any particular function, you change the function that you want to deal with, and that's it. I mean, you change. I mean, we can put here, now that we have all these kind of the bases developed, we can change the function and, you know, and do this very easily. But I would say that's more than enough to what I established to do, and I think that's it. As I always said, be safe, whatever be your final destination. Thank you. Bye.